We're back in the lab. So we have our hairdryer modified as a mass airflow sensor. So when air or breath goes through the hairdryer, it causes a change in the internal resistance. So we use this Wheatstone bridge here to measure that resistance by voltage division. The Wheatstone bridge is powered by the bench power supply. So the Wheatstone bridge is measured using a differential amplifier. Right now we're using a commercially available differential amplifier. So it has a gain of 2000. These are two inputs. Output goes to the oscilloscope. Now we're going to turn this thing on, go over to our power supply, fire it up, then we can go to our oscilloscope, see what's happening. So notice the oscilloscope was saturated negative and it jumped up, and now it's starting to come down. Like, see, the signal is slowly decaying down. It might be something familiar we've seen before, maybe in the RC time constant lab perhaps. Bring that back up. So our scale is 500 millivolts per division. So our zero is actually right here. So notice I move my baseline indicator down by turning the position knob on the oscilloscope, and that way I could see more positive waves, like more of the positive dynamic range, while being on a smaller voltage per division scale. So if I had the baseline indicator up here, I might be going off the top of the oscilloscope. So those are some of the adjustments that you can make. And notice how the circuit, it's still settling down, right? Like, that must have been when I touched something. And let's see what happens if I breathe into it. So just made a few breaths there, kind of sounded like Darth Vader. That's okay though. And I'm going to freeze the oscilloscope, hit the stop button. I'm going to save this waveform, and then that way we could analyze it later on. So there's an important thing to look at. So I saved it as a CSV. I'm going to save it as a picture just because sometimes a picture is worth 1,000 words or 1,000 data points. So now I have a picture of the screen and also the waveform here. And notice the drift is very slow. So you can see it's moving really slow. And the breath rate, is at a much smaller time scale. We're on 10 seconds per division. So, looks like we're getting about 2 or 3 breaths, per 10 seconds on there. And we want to build a modification to the circuit so that we could suppress the drift. And we'll talk about that in a little while. But the important thing to realize here is that the drift is really slowly acting in time. Notice it's moving, maybe like 100 millivolts over 30 seconds, whereas the breath signals, the period of the breath signal is maybe 4 or 5 seconds or even less. So the fact that those have different time scales allows us to use a filtering technique to filter out the really long time scale waveforms, but allow the higher frequency breath signals to pass through. So that's basically what this lab is about, is how to do that filtering.